Good afternoon. I'm Peter Goddard, Director of the Institute for Advanced Study, and it's my privilege to welcome you here for this commemoration of the life and work of Atle Selberg, who died on August the 6th, 2007, at the age of 90. Atle Selberg was one of the greatest mathematicians of the 20th century, and he represents a great part of the history of this Institute for Advanced Study. He first arrived here from Norway in 1947, just 14 years after the Institute had started its work. And he spent all but 2 of the next 60 years here as a member, or from 1951 as a professor. His contributions to mathematics are immortalized in the many concepts and results that bear his name: the Selberg trace formula, the Selberg sieve, the Selberg integral, Selberg class, Rankine-Selberg L function, Selberg eigenvalue conjecture, Selberg zeta function. In 1950, he was awarded a Fields Medal for his elementary proof of the prime number theorem. He received many other recognitions of his achievements, including a Wolf Prize in 1986, membership of the Norwegian Academy, the Royal Danish Academy, the Royal Swedish Academy, the American Academy of Arts and Sciences, the Indian National Science Academy, and honorary membership of the London Mathematical Society. The cases in the lobby of this building are displays relating to Atle's life and work, and we're very grateful to the Selberg family, both for lending the materials for this and also for their crucial contribution to the planning of this gathering. This afternoon and tomorrow morning, we have a program of scientific talks about Atle Selberg's achievements. Tomorrow afternoon, following a general talk by Enrico Bombieri, others of his colleagues and family will speak in personal terms about Atle. Our first speaker is KANNAN, SOUNDARARAJAN, who will talk about Selberg's contributions to the theory of the Riemann zeta function and Dirichlet L functions.
Thank you very much. It's a great honor to be asked to speak at this memorial meeting. Selberg was a great source of inspiration to me, and I think I was quite intimidated by him when I was here, and I did overlap with him, which I regret a bit now, but at least I did summon up the courage once to ask him to autograph my copy of his collected works, and I'm very glad I did, and that's a prized possession that I have. So today I'll tell you something about his contributions to the zeta function and L functions. The title is actually the title of some of his papers. So let me begin by recalling what the Riemann zeta function is. So we have a Dirichlet series 1 over n to the f, which can also be written as a product over primes. The product over primes is simply the statement that you have the unique factorization of numbers into prime numbers. And both the series and the product converge absolutely when the real part of S, which is usually written as sigma plus it, is bigger than 1. And Riemann showed that this function extends meromorphically to the complex plane. It has one simple pole at 1, and that pole has residue 1. Sorry? Can you tell me when it gets better? Is it better? No? There? Yes? Okay. And there's a functional equation which was proved by Riemann, which connects the values of the zeta function at S to the values at 1 minus S. And this just involves some power of pi and the Euler gamma function, like so. And since the gamma function has poles at 0, -1, -2, etc., one can see that there must be some trivial zeros of the Riemann zeta function at -2, -4, etc. The non-trivial zeros are denoted by rho, which is beta plus I gamma. And the fundamental problem in number theory is to understand the location of these zeros. So from the Euler product in the functional equation, from the Euler product, one can see that there are no zeros to the right of 1. And from the functional equation, it follows that there are no zeros to the left of 0. And that's more or less what we know. So there's a beautiful result of Hadamard and Delavalle-Poussin. This is the proof of the prime number theorem, which makes the modest saving that in the less than equal to, you can drop the equality. So the zeros lie strictly between 0 and 1. And the most outstanding open problem in number theory, and maybe also one of the most outstanding problems in mathematics, is the Riemann hypothesis, which says that all the non-trivial zeros of the zeta function lie on the line, the real part of s equals half. So much of what I'll discuss about Selberg's work revolves around this. So I should first orient you by telling you how many zeros of zeta there are. So you can count very easily the number of zeros with ordinate lying between 0 and t. Now, there are some symmetries of the zeta function. The functional equation tells you that the zeros are located symmetrically around the critical line, real part of s is half. And by complex conjugation, they're also symmetrically located around the real axis. So we can restrict ourselves just to the case where the ordinates are positive throughout. And the simple application of the argument principle allows you to count how many zeros there are. And the shape of this answer really comes from the functional equation here. The gamma function is one whose argument grows like t over 2 pi log t over 2 pi, and that's what we see as the main term for the number of zeros. And there's a quantity s of t, which will play a major role later in this talk, which is the argument of the zeta function at t. So you define the argument by taking the argument to be 0 on the real axis, like at a point 2, say, and then you continuously vary the argument until you get to 2 plus it, and then you see what happens to the argument as you vary continuously from 2 plus it to half plus it. Now, the first great results of Selberg on the zeta function go back to a paper that he wrote in 1942. It appears as number 9 of his collected papers. This paper is introduces a lot of new ideas. He proves the amazing theorem that you can actually get a positive proportion of the zeros of the Riemann zeta function lying on the line real part of s equals 1/2. The Riemann hypothesis tells you that all the zeros must lie on this line, but Selberg is able to find some proportion of them which lie on the line. And the second result that he proves is that he can locate almost all of the zeros in the sense of density, almost 100% of the zeros, within a very small neighborhood of the critical line. So I'll try to explain both of these results now. So suppose we denote by n0 of t the zeros of zeta which lie on the critical line, which conjecturally should just be n of t. The first result in this direction was by Hardy in 1914, that you can actually find infinitely many zeros which lie on this line. And subsequently, Hardy and Littlewood improved this to getting n of t, at least t zeros up to t, which lie on the line. And you're off by this factor of log t. And this proved to be quite an interesting sticking point. I mean, there were many, many proofs of the Hardy-Littlewood result by Landau, Siegel, Polya, Fekete, and others, but there was no real breakthrough over the t. So Selberg's result was the first time when somebody had gotten over t zeros. And in fact, first he proved that you could get t times log, log, log t zeros, which lie on the critical line, and then he was able to sharpen that soon afterwards to get t log t. In fact, due to some publication delays, his worst result actually appeared later in print than the better result of T log T. So how do we place these zeros on the line? So if you take a point on the critical line, and you take theta of t to be the argument of this factor which appears in the functional equation, then if you define z of t to be e to the I theta t times zeta half plus it, then what you see is that this is basically the same quantity as what happens in the functional equation, except for the magnitude of the pi to the s, pi to the minus s over 2, gamma of s over 2 has been taken out. So therefore, the functional equation tells you that there's a symmetry that z of t is the same as z of minus t. But if you conjugate both sides, you also see that z of t is the complex conjugate of z of minus t. So therefore, you conclude that z of t must be a real number. So in other words, we actually know what the argument of the zeta function on the critical line is, except for the sign, plus or minus. And then the idea is, now you have a real valued function whose zeros you want to understand. And this we can hope to do by just counting sign changes in z of t, and every time we have a sign change, we know that we have located a zero which is on the critical line. So for example, Hardy starts by looking at the integral from t to 2t of z of t and compares it with the integral of the absolute value of z of t. If there's no sign change, then both integrals must be the same. But on the other hand, you can show that the first integral is little o of t, so there's a lot of cancellation in z of t. The second integral, one can show, is at least as large as t. And so therefore, between t and 2t, you can get at least one zero of the Riemann zeta function lying on the critical line, and so there must be infinitely many such zeros. Now, if you want to get more zeros this way, then it's clear that what you have to do is not to have a long interval such as from t to 2t, but you need to be able to count sign changes in very short intervals. Now, this argument can be modified and was modified by Hardy and Littlewood to have, if you have intervals around t of length some power of t, then you can still show that there must be a sign change in every such interval. But when you have a very short interval which is smaller than a fixed power of t, that fails. It need not be true that you cannot prove that every such interval does contain a zero. So instead, what Hardy and Littlewood did was that they looked at an interval from t to t plus a, where a is some large constant, and instead of asking that every such interval contains a zero of the zeta function, they only wanted to know that for a lot of values of t, you can find a zero in such an interval. And here's how you can do that. So you do this by basically taking an L2 estimate. So if you look at this variation of the integral from t to t plus a of zeta of half plus iy, usually we expect it to be of size a. And they're able to show that on mean square, that integral is small, this integral, which tells you that usually, if you take the integral of the absolute value of the z function, then you get that it's usually of size at least a over 2. But on the other hand, you can take an L2 estimate of the integral of z of t without the absolute value, and then you can show that that L2 estimate is very small. So it's of size a times t. And what that means is that usually the integral without the absolute value is only of size square root of a. And therefore, you get that, let's say you can make this happen 99% of the time, that you get the integral of the absolute value being as large as a over 2, and 99% of the time you can make this smaller than a over 2. And so at least 98% of the time, you will have a zero in the interval from t to t plus a. Now the problem is that the Riemann zeta function has about t log t instead of t zeros. So if you want to prove Selberg's positive proportion result, you need to consider even smaller intervals than intervals of constant length. So you need to consider intervals of length about a constant over log t. So, and if you can get many such intervals containing a zero, then you would get t log t zeros as needed. And this is not possible to do by the Hardy-Littlewood method. And the reason for it is, well, you can do both estimates. You can take the mean square of the integral of z without the absolute value, and you prove a result similar to what I have here, similar to this result. And all that it tells you is that usually the integral without the absolute value is of size square root of a over log t. But on the other hand, you can show that typically, even if you put the absolute value, it is in fact not of this size. It is much smaller. And the reason for this phenomenon is roughly that if you take the integral of the second moment of zeta, then that's of size about t log t, but the first moment is not of size t log t to the 1/2. It's much smaller. It's of size only t log t to the 1/4. So in other words, what we see here is that the values of zeta are quite wildly varying. The first moment captures some of the behavior, but the second moment amplifies the larger values of zeta. And so since zeta doesn't have a uniform size, there is some loss when you try to estimate things using the second moment and the first moment. And this was a crucial idea which was introduced by Selberg to circumvent this. He uses something which he calls a damping factor. So actually, I don't think he calls this a damping factor anywhere in print that I've been able to find, but I think in conversations he somehow seems to prefer this term to describe something which we now usually call a modifier. And the idea of a damping factor is it's a quantity which is always going to be non-negative and which will have the property that when you multiply it by zeta of half plus it, you get a function which is usually of constant size, so that it will neutralize this discrepancy between the first and second moments that you see. And here's how he constructs such a damping factor. So you take this eta of t, which is given in terms of the coefficients of 1 over square root of zeta of s. So it's something that we can write down in terms of binomial coefficients. And the idea is to take a truncation of this series defining 1 over square root of zeta of s and hope that this truncation is usually going to be close to 1 over square root of zeta s. So in other words, when you take zeta of half plus it and multiply it by the absolute value of eta of t squared, our hope is that it'll still have some fluctuations in sign, but maybe the size of it is almost always constant. Okay. So now we can study the sign changes of z of t times eta of t squared. And this is the main result that Selberg proves. So he gets estimates for the L2 norms of both the integral over an interval from t to t plus a constant over log t without the absolute value sign, like here. And also proves that when you take this exactly as in the Hardy-Littlewood method. So for the integral with the absolute value sign, using this L2 estimate, you can usually say 99% of the time, you can get that absolute value is at least of size the length of the interval. And so now you have the result that you need. So most of the time, if you choose a large enough value of a, you can conclude that there will be, say, for 98% of the values t, you can find a 0 between t and t plus a over log t. And this, of course, proves that there is a positive proportion of zeros which lies on the line. And Selberg actually proved a little bit more. You can actually guess from this 98% that I wrote down that if you take larger and larger values of a, if you allow your interval to have slightly longer length, then almost all such intervals t will have at least one zero of the Riemann zeta function. So Selberg never really computed what proportion that he gets, and this was computed in an Oxford thesis by Min, who I think was a student of Titchmarsh, and it turns out that the proportion that you get from this is extremely small. This is one of the famous jokes of Selberg, that he liked to say that if a student named Max had computed the answer, then perhaps the answer would have been larger. So this is one of the main results in his 1942 paper. And the other result has to do with putting many zeros close to the critical line. So here the idea is to count zeros n sigma of t, where I'm interested in the real part of a zero being larger than sigma. Of course, we don't expect these zeros to exist because we expect all the zeros to lie on the critical line. So we are really, in some sense, studying the empty set, but of course we can't prove that it's empty here. So what we aim to do is to show that this set n sigma of t is at least not very big. There's a lot of people before Selberg who had worked on this. So Bohr and Landau were the first to study this, and Carlson and Ingham. And Ingham produced a very beautiful result on this, which says that if you're to the right of half, say at least half plus delta away, then you can get a saving in the power of t of how many zeros that you have which violate the Riemann hypothesis. And then in many situations, Ingham's result still has not been improved. So it's quite a striking result. And what it proves is that you can get almost all the zeros of the Riemann zeta function to lie within a distance of log t over log t, something which goes to 0 from the critical line. Now, Selberg makes an improvement to this, which is that he's able to narrow down this region and say that you can localize most of the zeros of the Riemann zeta function to be within essentially a constant over log t from the critical line. This looks like a little bit technical, but actually it turns out to be a really fundamental result. There's a density result that he proves, which is more precise in this context, which I'll mention, which turns out to be extremely useful and can substitute for the Riemann hypothesis in many cases. But also what I want to indicate here is the method that he uses to produce this result, which is again related to this idea of finding a damping factor. So here the idea is to find these numbers lambda n are arbitrary real numbers. And let's just normalize it by setting lambda 1 to be 1. And the idea is to minimize this integral of zeta of half plus delta plus it times this damping factor and its difference from 1. Suppose you could do this and prove that this quantity was always small, then what that's telling you is that zeta times psi is usually about size 1. And if zeta times something is usually about size 1, then that means that zeta cannot be 0. So that tells you that can be used to give these zero density results. Now, what Selberg notes is that if z is a small power of t, let's say t to the 1 over 20 or something like that, then you can evaluate this integral accurately. And let's say if you just look at the case where delta is 0, the shape of the answer that you get has the shape of being a quadratic form in the lambdas, because after all, it's a mean square which is being evaluated. And then we have a simple problem, which is you're given a linear form which is fixed. The first coefficient, lambda 1 equals 1, is fixed. And then you have a quadratic form in the lambdas which has to be minimized. And Selberg figures out how to solve this optimization problem by just diagonalizing the quadratic form that you have. And you can do this. And he finds that the choice of lambda n's is something like, is the Möbius function, which is not very surprising because if you have the sum of mu n over n to the s, that's roughly 1 over zeta of s. So it's some truncation to 1 over zeta of s, which this damping factor psi is, times some kernel log z over n over log z, which is also optimal. And this simple idea of trying to optimize this quadratic form actually turns out to be very powerful. And this idea is closely related to the idea of Selberg sieve, which John will talk about next. So these are the two main theorems in his 42 paper. And I can tell you some of the developments that came out of this. So in 46, Selberg proved analogs of these results for Dirichlet functions. So you can, certainly if you just fix a Dirichlet function, you can prove that a positive proportion of its zeros lie on the critical line. But he also proved more interesting analogs, like if you take a small interval near the real axis, say from 0 to a over log q, then he proves that if a is sufficiently large, then you can find many, many characters chi mod q having at least one zero in this interval, which lies on the critical line. Then in the 80s, Hafner adapted Selberg's method to prove that a positive proportion of zeros of modular form L functions also lie on the critical line. In the 70s, by a very different method, Levinson managed to put a very large number of zeros on the critical line. He managed to put a third of the zeros on the critical line. So the initial starting point of Levinson is different, but eventually you still use this idea of having a damping factor, which Levinson called a modifier. And I think this term somehow seems to have been inspired, and it's a term which is still which is more popularly used now. But one interesting consequence of Levinson's method, which was observed by Selberg and independently by Heath Brown, is that Levinson's method actually produces simple zeros of the Riemann zeta function on the line, whereas Selberg's method only produces odd order zeros. You can show, but you don't know that the zeros have multiplicity 1 exactly. But the two methods are quite different in spirit. For Selberg's method to succeed, this damping factor can have any size, whatever, and you don't need to make a calculation. The answer that you get might be bad, but in terms of the constant that you produce, but you will always produce a constant. In Levinson's method, you can, when it works, you can produce a big constant, but sometimes it just doesn't work. For example, it doesn't work for modular form L functions, as in the result of Hafner. So these ideas of using modifiers or damping factors are very central to recent work which has been carried out on finding zeros or vanishing or non-vanishing of L functions at the central point, let's say at half. So there's many people who worked on this, some of whom I've mentioned here. Now, the second result that I mentioned of Selberg in this 42 paper was this zero density result, putting many, many zeros within a constant over log t of the critical line. And a stronger version of this was given by him in 46, which takes this shape that if you're delta away from half, then the number of zeros that you have is a factor t to the minus delta over 4 better than the trivial estimate of t log t. So you can see that if delta is a little bit larger than 1 over log t, then you're producing a lot of, your estimate is a tiny fraction of the total number of zeros that we have. And again, an analogous result of this type was proved by Luo for modular form L functions. And while I'm still on the subject of zeros, I'll tell you this lemma of Selberg, which seems a little difficult to parse, I think. So the point is you have an analytic function, and if you're counting a big box, then there's a very simple application of the argument principle that you can use to count how many zeros that you have in a big box. However, if you have a tiny window in which you want to count the zeros of an L function or just any analytic function, then what you might want to do is to find the change of the argument as you vary over your box. But the problem is the horizontal line segment may be of almost the same length as your vertical line segment. And you don't want to face ever the imaginary part of the logarithm, because the imaginary part of the logarithm already encodes information about the zeros, and you want to avoid the imaginary part of the logarithm. The real part of the logarithm is friendlier because that's just related to the size of the function, which you can hope to estimate by some methods. So what you would like is a version of the argument principle where you can count the number of zeros in a box in terms of just the real part of the logarithm of a function. And that's what's provided by this lemma. You have this complicated function, which all we really care about is that it's positive. It's counting at least all the zeros in your box with some weight. And on the right side, you have an expression for it which is given in terms of the logarithm of the function, but you see you only have the logarithm of the absolute value of the function up here. So this is not a very difficult exercise in complex analysis. It's closely related to the idea behind the Fragment-Lindelof principle. But it turns out to be an extremely useful lemma. And in recent years, it's been used by Kowalski and Michel, and also by Michel and Heath Brown in problems involving low-lying zeros of L functions. And a few years back, Conry and I used it to prove that there are many quadratic Dirichlet L functions with no non-trivial real zeros. And this really crucially depends upon Selberg's lemma and also these ideas behind the modifier. Now, that's the story about Selberg's work in this 42 paper. Now I want to tell you something about a few papers that he wrote in 1946, 3 papers which have to deal with certain statistics involving the Riemann zeta functions. So I want to tell you his motivation behind these papers, which is still concerned with the Riemann hypothesis and the problem of putting zeros on the critical line. So once you have a positive proportion of zeros on the critical line, you could say that the next step forward would be to continue this to show that at least 100% of the zeros could be put on the critical line. But Selberg is pessimistic about this, and he says that this is unlikely to be proved by these methods because this would demand a much more regular spacing of the zeros of the zeta function than is really the case. So I want to explain why he says this and what it led him to, which is, in my opinion, as interesting as any of these results on putting a positive proportion on the line. So recall this function theta of t, which we used to create a real valued function on the half line. And by Stirling's formula, you can work out an asymptotic for this. It's about size t over 2 times log t. So there are some special points of this function called gram points, where it takes a value which is an integer multiple of pi. So that if you have e to the I theta t, then you get either +1 or -1. So these gram points are, of course, very evenly spaced. It's very easy to work out an asymptotic for them. Now, at the gram points, our function z of t is just plus or minus zeta of half plus it nu. And there's a formula that you can write down for zeta of half plus it, which is called the Riemann-Siegel formula. There are many ways in which you can do something like this. But the crucial thing is to note that it starts with a 1, and then it has various signs, various terms which are oscillating in sign. So we can imagine that the terms which are oscillating in sign are more or less canceling out, and let's pretend that they don't exist. If they don't exist, then we have that zeta of half plus it nu usually looks like 1. And let's say, maybe even if it's not close to 1, we might expect that it's usually positive, let's say. If that's the case, then we would have, for 2 consecutive gram points, that the z function would be positive at one and negative at the other. And therefore, there would be a 0 of the Riemann zeta function between these 2 consecutive gram points. If this picture were to hold, then you would get the right number of zeros of the Riemann zeta function lying on the critical line, and you would basically be able to prove the Riemann hypothesis. And it seems to be true, at least initially. So I think the zeros up to 100, there is exactly a 0 between every 2 gram points. And Titchmarsh had done some computations on this, and he found that it's usually true even if you go up to 1,000. So this was in the days before a computer, so I guess 1,000 was still some fair degree of computation. It fails, there are about 1,000 cases, and it fails about 40 times. But what Selberg realizes is that there are actually substantial differences in the substantial irregularities in the distribution of the zeros of zeta. And what he proves is that the nth zero of zeta, if you look at the ordinate of the nth zero, which is gamma n, it never lies in the nth gram interval from Tn to Tn plus 1. So in other words, if you try to prove the Riemann hypothesis by trying to find a sign change in a very regular way, you're never going to be able to succeed. And what he also proved was that if you look at the consecutive spacings between the 2 consecutive ordinates, gamma n plus 1 and gamma n, there are t log t zeros up to height t, so the zeros are getting closer and closer to each other. So you multiply them by log gamma n, which is about a log t, to make sure that the spacings are usually of size 1. And then what he proves is that some of the time, the nearby spacing is a little bit larger than 1, and some of the time it's a little bit smaller than 1. So they can't be regularly spaced like an arithmetic progression. And this is, of course, part of the reason why he believes that you will not get 100% this way, because if you take a short interval from t to t plus a constant over log t, it could happen from time to time that there would be 2 zeros which lie in that interval, and you would have only counted that as one sign change by the method that he uses. And so you will certainly miss quite a few zeros this way. So how does he prove this result? So I started out with this formula for the number of zeros up to height t, which has some main term and has this remainder term, which is s of t, which is the argument of the zeta function at height t. This argument usually doesn't get very big. It's only of size about log t. And if you assume the Riemann hypothesis, you can make a modest saving over it, a log t over log t. And it was known due to Titchmarsh that this argument can fluctuate. It can go off to infinity, and it can also go off to minus infinity. But Selberg proves this remarkable result that if you look at the distribution of the argument, so it's pi times s of t, then the distribution is approximately Gaussian with mean 0 and variance half log t. So what this means is that because this variance is usually very large, usually this quantity s of t is something which is fairly large. It's of size square root of log t, usually. And that means that usually, if you look at the nth zero, it's going to be some distance away from the nth gram point on a scale of square root of log t from the nth gram point. So you're never going to get gamma n in this interval Tn to Tn plus 1. And the way he proves this is that he computes the moments of s of t, on which you can see that this main term that arises here, these are the coefficients of the Gaussian moment. And so since the Gaussian distribution is determined by its moments, you can conclude this result. This paper is really, so this is carried out in 2 papers in 1946. The first one proves this result conditionally assuming RH, and then he has to work very hard to remove RH and prove this unconditionally. And it's here that the zero density result that I mentioned of his comes in very useful. It allows him to completely circumvent RH in this proof. Here's the briefest idea of the proof. So if you just look at the logarithm of zeta half plus it, you have a sum over primes of the logarithm of 1 minus 1 over p to the p to the half plus it. You take a Taylor expansion for it. That series doesn't converge, but you can truncate it somewhere and hope that that still is approximating the imaginary part of the logarithm. So that's the truncated series here. And what Selberg is able to prove is that most of the time, this truncated series is actually a good approximation to S of t. This argument is quite remarkable. It's still a very difficult and hard to follow argument. I mean, every time I have to reconstruct it, eventually I have to go back to Selberg to figure out the right way to do it. The main idea is to express S of t in terms of primes and zeros of zeta, and then he does some magic by which he's able to transform the zeros back into primes, and then he's able to evaluate the contribution of the primes. And he also proved similar result for the real part of the logarithm, so which is just the size of zeta half plus it. And he proved again that this is also distributed like a Gaussian with the same mean 0 and the variance half log t. And moreover, the distributions of the imaginary part of the log and the real part of the log are independent. Statistically, there's no correlation between them. And this result is very beautiful and has led to work by many, many authors. I'll give you one version of this, one variant which is due to Fuji, which is that if you look at an interval from t to t plus h, where h is fairly small, less than 1, but h times log t goes off to infinity, then the number of zeros in that window has a Gaussian distribution with mean, which is the expected number of zeros, h over 2 pi log t over 2 pi, and variance, which is a logarithm of this h log t. So one thing that you can see here is that the variance is very small compared to the mean that we have. If you have distribution of random numbers thrown down, then the variance typically there would be roughly of size equal to the mean. Whereas here you see that the variance is of size only the logarithm of the mean. So this is a hint of an interesting phenomenon. And in general, in all of these works, Selberg seems to have come very close to asking a very basic question, which is, what is the distribution of spacings between zeros of the zeta function? So his result on the lim in for the lim sup being removed from 1 is one consequence of understanding what this distribution would be. Well, the question seems to have been first asked by Montgomery, and it's this famous pair correlation conjecture of Montgomery, supported by experiments of Odlyzko. And what this has led to is the idea that the spacings between zeros of the zeta function correspond to spacings between consecutive eigenvalues of large random matrices. Let's say unitary matrices chosen with respect to Haar measure. Now, random matrix theory has proved to be very useful in understanding properties of the zeta function. So I want to tell you one example of that, which is the work of Keating and Snaith, which is actually which is influenced by Selberg's theorem on the Gaussian distribution of log zeta half plus it. So Keating and Snaith started by noting that you have Selberg's theorem, which says that these objects are Gaussian. But even if you take a large value of t around size 10 to the 20, and if you compare the distribution of log zeta of half plus it at that height to the Gaussian distribution that is the theorem, then the fit of the numerical data to the theory is not very good. This is kind of startling because you have conjectures on the spacing of the distribution of gamma n plus 1 minus gamma n, and the fit of the conjectures to numerical data is excellent. You don't see any difference between the theory and data, whereas you have a theorem here which has very poor fit with numerical data. And what they wanted to know was whether you can explain this deviation of Selberg's theorem from the numerical data by some systematic way. And they formulated a more refined model which says that if you're interested in properties of the zeta function near height t, then you should consider not large random matrices. In other words, you shouldn't let n go to infinity, but you should pick a particular value for n. And the value for n that you should pick should be that n should be of size about log t. And the reason is, if you have a unitary matrix of size n, then you have n eigenvalues constrained to lie between 0 and 2 pi. So the mean spacing is 2 pi over n. And if you're looking at zeros at height t, the spacing between two consecutive zeros is 2 pi over log t. And you should naturally set these two quantities equal to each other. And that tells you what n should be. And this was a very insightful observation which led to a solution, well, at least a conjectural solution to a problem involving estimating moments of the Riemann zeta function on the critical line. So you want to get some asymptotic formulas for the 2kth moment of zeta. And we only know how to do this for k equals 1 and k equals 2, which are classical results of Hardy and Littlewood and Ingham. There was a folklore conjecture that the kth moment should be of size some constant times t log t to the k squared. And we had some idea of what this constant should be, that it should factor nicely as a product of some geometric quantity gk, which is an integer, times some arithmetic quantity ak, which is easy to understand. But it was not clear how to guess what the constant gk should be. So we know that g1 is 1, g2 is 2, and Conry and Ghosh managed to conjecture that g3 is 42, and then it took a lot of work to conjecture that g4 is 24,024. It didn't seem clear how to extend these computations. But if you use this model of Keating and Snaith, then what you should look at is you can model the absolute value of zeta half plus it by the characteristic polynomial of a random matrix, G, which is chosen. So you look at the determinant of I minus G, and you want to ask in random matrix theory, you would like to know what the average of the 2kth moment is as when you pick a random G. Amazingly enough, when you try to evaluate this integral, you land up with an integral which was evaluated by Selberg and published in a journal for high school teachers, I think, in Norwegian. So I think Peter will say something about this tomorrow, about this integral. And then they managed to find a conjecture for what GK is. So in the course of this work, they were also led to conjecture an analog of Selberg's theorem on the Gaussian distribution in families of L functions. So I'll give you one particular case of their conjecture, is that if you look at quadratic Dirichlet L functions, so these are generalizations of the Legendre symbol, and if you look at the values of log of L half chi d, then there should be some analog of Selberg's theorem that these should be also look like Gaussians with a mean which is not 0 in this case. It's a little bit shifted, which is half log log x, and variance, which is about size log log x. We cannot quite prove this, but if you assume some small amount, something about the distribution of low-lying zeros of these L functions, then you could use Selberg's method to prove some Gaussian distribution of this type. So, but returning to these moments, you can get lower bounds of the right order of magnitude for the moment, which is an old result of Titchmarsh. And recently I was able to prove that you can get an upper bound. If you assume the Riemann hypothesis, you can get an upper bound for the moments, which is only an epsilon away from the right answer. And the basic idea for this method, for this result, is also largely based on Selberg's theorem. The idea is that if you can understand the distribution of the large values of zeta, then of course you will be able to bound the 2kth moment of zeta. So you really need to understand the measure of the set on which log zeta half plus it is bigger than some quantity v, say. This is exactly the sort of thing which is covered by Selberg's theorem, but in the region when v is fairly small, like square root of log log t. But if you could prove a version of Selberg's theorem uniformly in a wide range, then you would be able to use that result and be able to understand everything you want to know about moments. And what I was able to do was to adapt Selberg's techniques to prove such a uniform result, at least a one-sided version of it, and that leads to these bounds and moments. So these 46 papers of Selberg's have had a lot of impact on the field, and I think they're still continuing to have a lot of impact on the field. Now, finally, I want to say something about later work of Selberg, his 89 Amalfi paper, which also introduced a lot of new ideas in the field, where he axiomatized properties which we expect of zeta functions, like the Euler product or the functional equation, and formulated several conjectures on this, that that the size of the Dirichlet series coefficients at primes should be independent for different L functions in this family. So this is what's called the Selberg class, and this has also inspired a lot of work by Conry Ghosh and the Murthys and Kaczorowski and Perelli. And there are lots of very interesting results which have been proved by Kaczorowski and Perelli. So one thing is that they have been able to characterize the elements of degree 1 in the Selberg class and find that they are only the Riemann zeta function and Dirichlet L functions. And recently, it seems they've been able to prove that there are no elements in the Selberg class up to degree 2. And if we could understand what happens in degree 2, then that would be a very big step forward. In the Amalfi paper, Selberg also studies the value distribution of log f of s, as in log zeta of half plus it, for values of s on the critical line or very close to the critical line. And he shows that if you take two different L functions, f1 and f2, then the distribution of the logarithms are statistically independent for different L functions. He also makes a study of the A points. So instead of looking at the zeros of f of s, he looks at the points where f of s equals a for some non-zero value of a, and studies where these points, the distribution of these points. And lastly, makes a very interesting study of linear combinations of Euler products. So you take n different L functions, L1 to Ln, and you form, and let's say they all have some Dirichlet series and they all have some Euler product, and they all have a functional equation, and we have to assume that they all have the same functional equation. So for example, they could be L functions associated to the characters mod q for some fixed value of q. And if that's the case, then you could look at linear combinations of these n L functions, and it turns out, it's a beautiful paper of Bombieri and Hegel, that if you assume the Riemann hypothesis for all these L functions and some other natural conjectures on the spacings of their zeros, then you can prove that almost all the zeros of these linear combinations also lie on the critical line. And this is a little bit strange because you have a situation where you almost have a generalized Riemann hypothesis, but these linear combinations really have no business satisfying a Riemann hypothesis. And they, in fact, have a lot of zeros, not of positive proportion, but still a fair number of zeros which are not on the critical line. And one of the ideas which is introduced in these works is that the linear combinations of such L functions are usually dominated by a single L function. And the reason for it is you have these n L functions, and if you look at the logarithms of these, each one of these is a Gaussian with a large variance. So each one of these will have some large size, but pick the largest one of that, and that will be much larger than everything else. And in a small region around that point, that single L function is going to dominate the behavior of this linear combination. There's been a lot of work on finding zeros of these linear combinations by Warren and Karatsuba, Hegel, and Bombieri and Hegel. But the last word on the subject rightly goes to Selberg. And about 10 years back, he proved that if you take for many of such linear combinations, when the degree is at most 2, he goes back to his first result on a positive proportion of zeros of the zeta function, and he's able to prove the same result in this case, that you can get a positive proportion of zeros unconditionally, which lie on the critical line, which is quite an amazing feat. It combines all these ideas of both the Gaussian distribution, knowing that only one of these is going to dominate at any point of time, combined with this idea of the damping factor which he introduced previously. So unfortunately, this is still unpublished, and I hope that some version of it will appear, will be written up soon. Well, thank you very much.
I'm pleased to introduce John Friedlander, who is going to speak on Selberg and the sieve, a positive approach.
Thank you. No? Okay. Well, I'm very honored to be invited to participate in this conference in honor of one of my great heroes. So, start with that. And every lecture should have some little amuse-bouche for some people who don't want to pay attention, that so they can spend their time wondering, this does not represent the grade I'm giving myself for this lecture. That's a hint I'll give you. I suppose I should start with the odd numbers on the left, so I'll know what I have a better chance to remember what I'm doing. No, actually. Okay, so Selberg did very fundamental work on the sieve, but he was actually not the first person to work on the subject. So we'll begin with a little review, which sieve begins with Eratosthenes about 300 years BC in Alexandria, which was the Princeton of the day. So let's begin with the integers from 1 to x, where x is 30. And we cross out all the even numbers. And then we go to the next prime number, the first uncrossed number beyond 1, which is 3. We cross out all the multiples of 3. We then look to see what's the first uncrossed number is 5, and we cross out the multiples of 5. And at this point, we notice that since every number which is not prime must have a divisor smaller than a prime divisor, in particular, smaller or equal to its square root, that we've passed the root of 30, so we can stop and say, okay, all we've got are primes. So now if we try to count what we've done in this situation, we've started with the integer part of x, that's the greatest integer less than or equal to x. We've removed the multiples of the primes up to square root x. Sometimes, like here, when we get to the next prime, we see we're removing some guy for the second time, so we have to add it back in. The number of multiples of each pair of primes. And then we see, oh, here's one we've got to where we started with it, we removed it 3 times, then we added it back in 3 times, but we don't want it there, so we have to remove it again. Well, this reminds us of the Möbius function, which is defined as follows. It's defined on square free numbers, integers having only distinct prime factors, and it's -1 to the number of these prime factors. If we define, as usual, the prime counting function pi of x, then what we've wound up with over there is we've wound up with the integer 1. We've wound up with the primes up to x, other than those that were less than or equal root x. So this leads us to the Legendre formula. And we'd like to count pi of x. We'd like to. And so fortunately for us, pi of root x is rather small because it's certainly less than the number of integers less than or equal to root x. And that turns out the number of primes are much larger than that, so we can neglect that. So the right-hand side should be a good approximation of the number of primes. When we see the integer part of x over d, about all we can do with it, though, is replace it by the simpler looking function x over d, and that leads us to the following formula, which we can write as a product, and where the remainder is given by this sum, where the curly brackets, as usual, are the fractional part of an integer, of the real number inside. Since that quantity is always less than 1, we can say our remainder is bounded by the number of divisors we've been looking at, but that's 2 to the pi of x, and that's really a huge number. Well, we've been pretty stupid so far. We crossed out multiples of d where d was bigger than x, which wasn't quite a very smart thing to do. So we could improve this. But the fact is the remainder here actually is the same order of magnitude as the main term. We know that because we know the prime number theorem, which we didn't prove in this fashion. So the sieve veritas then has remained largely a relevant tool for a couple of thousand years, and about 100 years ago, Viggo Brunn started the process of improving matters. One observation is that we don't need to sieve right up to root x. If we just sieve up to some smaller part, z, in this talk, z and z are the same thing. And that we can still get some useful information because it turns out if we have an upper bound, then we've got an upper bound a fortiori for our function pi, the thing we want to count. And if we have a lower bound, if we sieve up to any positive power of x, then we find that we've produced integers with few prime factors. Well, we also notice by this inclusion-exclusion that if we stopped after an even number of prime factors, we have an upper bound, and if we stop after an odd number, then we've got a lower bound. Okay, well, this is still pales compared to what we see from the prime number theorem, but the point is that this method generalizes to apply to sequences where the relevant Dirichlet series, the analytic machinery, hasn't got much chance, at least. So let's talk more generally. We'll take a sequence of non-negative reals, an, and a set of prime numbers. It's convenient to denote P of z as the product of these. And our goal is to estimate the sifting function, the sum of these AMs, over those M which have greatest common divisor with P of z equal 1. They're relatively prime to P of z. In other words, they're not divisible by any of these primes. Our basic property of the Möbius function is this summation formula, and we also know from elementary number theory that the set of integers which divide, the set of divisors of two integers a and b is identical with the set of integers which divide their greatest common divisor, AB. And so if we plug this in and interchange the order of summation, we're led to this formula here. And that's just the same as the Legendre formula we had over there, except in this, up there, except in this more general case. So we need information then about the inner sum, ADX. And ADX is just this congruent sum is the amount, the mass of that part of the sequence which comes from multiples of D. So in our first case, we're going to assume that it has a simple formula of the following shape: a main term plus a remainder term. In our example, the mass of coming from multiples of D was the integer part of x over D. It was approximately x times a function of D, which is simple, and it had a remainder which was small, less than 1. And in general, that's the case. Our A of x is something which is an approximation, like x was, to the integer part of x. And g of d is a nice function like 1 over d. We call it a density function. G of 1 is 1. It's multiplicative, and it's between 0 and 1 in values, and it's less than 1, because if it was equal to 1, that would mean everything in the set was divisible by p, and then we wouldn't look for primes there. Okay, R of D is our remainder, and we're hoping it's small. Well, there are numerous examples of sequences where we can apply this machinery or set it up like this. So far, there's really no machinery. So for example, we could take A to be the characteristic function on integers of the form n squared plus 1, where, say, n is even, but not necessarily. In this case, if the prime p is of the form 4m plus 1, then in every block of p, 2 of these guys is divisible by p, and if the prime p is anything else, then there are none of them. And here, if we could sieve up to root x and get something left behind, then we'd give primes of the form n squared plus 1, and it's a famous question whether infinitely many of those. The next two examples are approximations to the twin prime problem. We could start with a set of integers of the form n times n minus 2 up to x and say let n be odd. And in this case, for every odd prime, each block of p contains 2 multiples. So we'd have this, but for function g, but for every prime, odd prime. And now if we could sieve up to fourth root of x, we'd get twin primes. We could start with a set of integers of the form p minus 2, where we already knew p was a prime. P is always a prime in this lecture, unless it's in the middle of a word. And the density function is 1 over phi of d, and the number of multiples of d is the number of primes which are congruent to 2 mod d. And okay, so let's go back to this Legendre formula. And there it sits. And now if we input this approximation that we've assumed for our function, our congruent sum a sub d, then it looks like this. And this was based, as we said, on our basic property of the Mobius function. And we'll refer to this sum, if we call this sum over the divisors of n and mu of d, this function, let's call it theta naught of n. Now, suppose we could replace the Mobius function by some other functions, which I'll call lambda d plus or lambda d minus. And we're going to assume at 1 these are 1. I didn't write that down, but it turns out to be a useful assumption and that doesn't lose anything. And we define theta plus as being the sum of the lambda pluses. And suppose we knew that for all n we had this inequality, and suppose with the other guys we knew for all n we had this inequality, which means that these guys are 1 at 1, these guys are always greater or equal 0 afterwards, and these guys are always less than or equal 0 afterwards. Well, we could go through the same manipulation that we went through here, but now instead of with mu, with these functions lambda, and we get upper bounds, as written on them. We get upper and lower bounds for the sifting function we were trying to estimate, and they'd look exactly the same with the different coefficients. They'd look exactly the same as the other one. Now, the good thing about this is what happened before. We had this Möbius function that was given to us by God, and we couldn't change it around. It was there, and it went on forever. And because it went on forever, our remainder term was too big for us. But these guys we're creating out of nowhere. And now we can hope at least that we can force this remainder smaller by just insisting that these new sequences we're getting, these new sifting functions, these new sifting weights, I should say, are going to vanish beyond a certain point, capital D. We just proclaim that we're not going to accept any sequence which doesn't do that. Well, how do we get such a sequence? And the way Brunn started off was, remember, nu of D is the number of prime factors of D. He just truncated after a certain even point to get an upper bound sieve, or truncated after an odd number of prime factors to get a lower bound sieve. Well, this was done, I guess, in the 19-teens. Brunn worked and refined his method quite a bit. That was just his first method, and he went on to improve it. Other people, such as Ustab and others, worked on it until before the 1940s, and then at some point in the mid to late 1940s, Selberg got involved in this, and Selberg approached the sieve in a positive direction. He had a positive approach to the sieve. He approached it through the upper bound sieve. He invented what is called the lambda squared sieve by him, and was called the Selberg sieve by almost everybody else for half a century or so. Let's just start off with some set of real numbers, and they're defined on these integers that are made up of these products of primes. And we'll start with one that's 1, and we'll insist again that it's 0 beyond a certain point, perhaps z, the same z that occurs here, or perhaps a later point. And then for any integer n, we have the following property, which is just what we wanted for an upper bound sieve, and it's trivial that this is the case because squares of real numbers are greater or equal 0, and the first one was chosen to be 1. So now we input this creature into that same argument we used before, and we interchange the summation. Oh, I can't read my watch. That's going to be tough. And then we get a formula like this. Now, if you look at that, it doesn't leap out at you at first glance that this is an upper bound sieve. I mean, it certainly is in this sense. It gives you an upper bound, but it doesn't leap it out that it's of the same form of the sieves we've been talking about. but if you give it a little thought, you'll see it. This is the form we wanted it to be in, and it is of that form where the lambda d's are made up out of the rows by this slightly complicated looking formula. Here, the square brackets denotes the least common multiple, so this is a sum over pairs of integers in our set of divisors whose least common multiple is d. And note that if these guys, if the rows vanish after z, then the d's vanish after z squared. So they do vanish, or is w becomes w squared. In any case, they do vanish after a certain point, which we can control. And so now we do have sequences like this, because we can take rows to be anything. And we'll call, in general, we'll call D the level of the sieve, the point at which the sifting weights disappear. Now, if I look at that formula, my main term now is the mass, A of x times q, where q is a quadratic form in our density function g of d, in our rows, weighted by our density function. This is a quadratic form in our rows, and we want to minimize it because we want an upper bound, and we want the best upper bound we can get. So we want to minimize it, and this should remind you a little bit of Sound's talk on the zeta function, or part of his talk. And this extremal problem can be solved. We start off, we can diagonalize the form by defining for square-free d, we define h of d to be this product over the prime factors of d, where g was our density function. And then, given this h, we define these coefficients little y sub d. And after Mobius inversion, we can solve for the rows in terms of the y's. We get this. And after we've done that, our problem becomes minimizing this quadratic form, which is now diagonalized, subject to a certain constraint. So here's the constraint, and this the constraint we had before was that rho of 1 was 1, and it's transformed under these transformation to this. So here we have a quadric surface. I forget how many dimensions you need before you stop calling a quadric, subject to, you want to minimize it on this hyperplane, on this plane. Okay, so this can be solved in a number of ways, and I believe Selberg used Lagrange multipliers, for example. And the final result is, if we define this function capital H, then if we define this function capital H as the sum of the little h's, then the minimum of the quadratic form is given by H inverse, and the y sub d that give rise to it are also all given by H inverse. And then rho of d, substituting in that formula back there, is given in terms of the y's, so we can actually find the row of d's. And these are, this is not quite identical with this gives rise to sifting weights that are not quite identical with the ones that Sound wrote down in connection with the zeta function problem, but they're very close approximations. Okay, so now let me give you just a sample application of this. There were many applications, many results of Brunn and his successors were improved by Selberg's work. And here's an example of an important example of one, is that Brunn proved that if you looked at the set of primes in a short interval, so this makes sense when y is rather small compared to x, then you get an upper bound like this. And Selberg's introduction showed that any c greater or equal 2 would do, at least if the variables are large. Okay, so Selberg, as he records in his lectures on sieves, spent some time trying to improve the constant 2. I mean, now we all know that this can't be done, but this was 60 years ago, and it wasn't so well known then. And this led him to a lot of his subsequent work in sieve theory, and in particular to what he calls the parity principle. So let me give you, in particular, these are very simple things. I should say I'm trying to simplify in this lecture, and I hope I'm not doing too little justice to the depth of Selberg's work on the sieve, because I'm trying to illustrate the simplest possible things in connection with it. Suppose we take the set of integers a up to x for which have an even number of prime factors. Well, that set has no primes in it. But on the other hand, one can show that if you look at the various standard assumptions that people make in trying to estimate things using the sieve, that this set A satisfies all of these. And moreover, the remainder term, I wrote error term, I mean remainder term, the remainder term bound holds with D essentially as large as possible. So this example shows you that in some sense, unless you use some very specific information about the sequence you're looking at, information which just isn't within the sieve mechanism itself, then you're not going to find primes. Similarly, in the same fashion, you could look at the set of integers for which have an odd number of prime factors. Well, this set, in some sense, contains twice as many primes as it should. So if that's the case, then how are you going to improve that constant 2? Now, this is just a simple glimpse. Selberg spent a fair bit of time, I think, over the years subsequent to this, thinking of examples which show the limitations to what one can achieve with sieve methods, and he was extremely interested in this topic. These ideas also led him, as he himself mentions, these thoughts also led him to try to construct a local sieve, by which he meant a sieve which only worked when you had a set of integers which had essentially almost full density. Let's recall the definition of the von Mangold function, which is defined on powers of primes p to be log p and 0 elsewhere. And one can define in an analogous fashion, as Selberg did, the function lambda 2, which picks out in a similar fashion those integers which are products of 1 or 2 primes. And it's well known that the prime number theorem is equivalent to this asymptotic formula for the von Mangold function, in the sense that one can go relatively painlessly between these two facts. Now, Selberg showed that you can get an asymptotic formula for lambda 2, the sum of lambda 2 as well. It's asymptotic to 2x log x. Well, actually, if you use the prime number theorem, this is almost trivial to deduce, but the fact is Selberg found a way to do it without using any of this stuff. He found a completely elementary way to do that, and that led him to elementary proofs of Dirichlet theorem and prime number theorem, and I hoping we'll hear much more about this in a lecture tomorrow. And it later Bombieri developed these ideas very extensively as into a powerful and versatile tool, to quote Selberg. Okay, well, there are, however, such things as lower bounds, and whereas, if you recall, the Brunn's method, at least the beginning one, which is the only one we touched on, gave a very symmetric treatment to the upper and lower bounds. But with the Selberg sieve, it's just not symmetric. I mean, squares only come at you from one direction. And so it was important, because the best upper bounds at the time were coming from Selberg's upper bound, it was important to try and get lower bounds from them as well. Fortunately, there was a certain recurrence formula that had been noted by Buchstab and used actually to improve Brunn's bounds that had been given some years before Selberg's work. And it's very easy to describe. If we're given a sequence of A and parameters, say Z1 and Z2, we consider the difference, and these are the elements which survive the sieving up to Z1, but don't survive the sieving up to Z2. And if we group them in accordance with the least prime which removes it, then such an element is of the form AM, where M is divisible by P, but by no smaller prime in our set. Then we can write that fact, we can record that fact as this equation, where A sub P is the set of those multiples of P. And there's a minus sign here. So if we have a good way of getting upper bounds, as we did from the lambda square sieve, and we have upper bounds there, that'll lead to a lower bound here. Well, that's true if we can get this guy. I mean, what's the point of having a lower bound? We need a lower bound for here. This guy's not there with a minus sign. But the fact is Z1 is smaller than Z2. And as you can believe, that if Z1 is small, then Brunn's method, and even the sieve of Eratosthenes, works not too badly. If we aren't sieving very far, then our remainder term isn't building up. So we can expect good results. Okay, so. Okay, so let me recall our formulas for our upper and lower bounds. We had a main term and a remainder term, and the sum over D ran over these things. And, oops, oh no, now I'm in trouble. John, you've got a fat hand. Okay. This diagram, let me introduce the parameter. S is log D over log Z. And this diagram represents how close we can come to what we want. So this 1 represents the expected. Our expected answer is that the sifting function is the mass times this probabilistic expected quantity. And what we actually get for this sum in the main term is not 1 here, but for the upper bound we get this capital F of S, which is bigger than what we want, and worse than what we want, and what we get for the lower bound is also worse by something which is less than 1. But still, getting such results, just the fact that this diagram exists, the proof of existence of this diagram, which I didn't do, is a proof that we get an upper bound of the right order of magnitude, and a lower bound being positive implies almost primes in our set. That means integers with a bounded number of prime factors. It's easy to see that we want D to be large, so we want S to be large, so we're closer to the truth. And that'll happen if D is large, and it'll happen if Z is small. On the other hand, we'd like to sieve as far as possible, so that means we'd like Z to be large. So that's sort of a contradiction. So there's reasons we want Z to be large and reasons we want Z to be small, but we want D to be large, period. Well, the constraint on D is we want the remainder term to be small compared to the size of the main term. In our examples and in most cases, the main term in the sieve is going to be like ax over log x or log squared x or something like that. It's going to be that in all of the examples I gave. And here's the remainder term, the remainder, which we're hoping is small. And so we want that remainder to be like this, and we want to choose D as large as possible so that that happens. We can't expect D to be larger than X. In practice, lambda D is bounded by 1, and so what we could do would say, well, this is bound. It's not quite true that it's bounded by 1, but it's almost. It's small. We could say, well, this is bounded by this, so it's enough to show that's small. And for a long time, that's what was done. In more recent work, it's been possible to go further. And so without any prejudice at all, I mention as an example of such a result the theorem of Ivanets, which was one of the first that did that there are infinitely many n's such that n squared plus 1 has at most 2 prime factors. Okay, now to mention the next results I want to mention in connection with Selberg's work, I have to introduce the notion of what Selberg called sifting density, and which is also called by some other people the sieve dimension. Now this is, I should say, all along I'm adopting some of Selberg's notation, but not all of it. Notation in sieve theory is, there are far more names for things in sieve theory than there are things. So, but let's recall our density function, g of d, which occurred in our main term. The main term was here. And we're going to assume that it satisfies an asymptotic formula like this, where kappa is a certain non-negative constant. And this constant is what we'll call the sifting density or the dimension. In the case of all our examples, such a formula holds. In the case of our examples, g of p was either 1 over p or 2 over p or 1 over p minus 1. And it's an old theorem of Chebyshev that such an asymptotic formula holds in this case with kappa equals 1. I should say that there are other forms of this assumption, both stronger and weaker, that are sometimes more useful in this connection, but I'm mentioning this particular form, and usually any and all of them can be verified in any example you want to look at. So Selberg was very interested, extremely interested in the theory of the sieve. And here's an example of a theorem in his lecture notes, published in his second volume. Suppose we assume that the remainder term is satisfactory, and let's let d, we have this is true for x to the alpha for some fixed alpha, and that the sieve problem has a specific dimension kappa. Then under these conditions, he proved there are optimal upper and lower bound sieves for this problem. in the case where the remainder assumption holds, for every alpha less than 1, which, as I said, is the most you can hope for, then the optimal sieves can be given explicitly and are. I should mention that this statement, as many of the other statements I'm making, is only an approximation to the precise statement. And Selberg really was extremely interested in the situation where the sifting density is not constant, and that made the problem much harder. I think not many other people have studied that situation as far as I know. In order to talk about the next thing I want to mention in connection with Selberg, I need to introduce the notion of the sifting limit. And I'll reproduce the diagram we had a few slides ago, brought to you by the miracle of photocopying, which recorded, remember, this recorded how far away our upper and lower bound sieves were from giving us what we wanted, what we expected probabilistically. Now there's an important feature in this diagram, that the lower bound is 0 up to a certain point because you're counting things, so you can't do worse than that. And after a while it becomes positive, and this constant, this value of s at which it becomes positive is known as the sifting limit, and of course it's very important because it tells you, for a given d, it tells you how far, once you know that you can get the remainder small at a certain level d, it tells you how far with z you can sift. So, problem, what is the best one can do? What, if you use the best sieve you can for a given problem, what will beta be? And it turns out that this depends on the sieve dimension. It's been known for some time, in part due to Selberg's work, that the best you can do when the constant kappa equals 1 is beta equals 2. And in the case where kappa equals a half, the half semilinear sieve, then one can take beta equals 1. And perhaps these are the most important cases in practice, but it's also very important to know what's true when kappa's large. And the guess is that the conjecture is that beta kappa equals 2 kappa. Well, there's 2 cases. Let's assume that's true infinitely often, always. Or at least that it's asymptotically true for large kappa. Now, there are upper and lower bounds for this of the form a constant times kappa, but they were rather far from the truth before many people in this room gathered in Oslo to celebrate Selberg's 70th birthday. Now, before I get to Selberg's result, I have to mention an idea of his which involves combining 2 or more sieves. Now, suppose we're given 2 sequences of real numbers defined, the first guys are equal to 1, and they're defined on integers made up of prime factors in this set, square-free integers, and these are real, and then from these we form this new guy, lambda d, by combining these 2 and taking this sum. In general, this isn't a sieve, by which I mean it's not an upper bound sieve and it's not a lower bound sieve. Of course, if we take these 2 equal and call them rho d, then we get the upper bound sieve we talked about a while ago, the lambda square sieve. But in general, that's not a sieve at all. Suppose, however, we start with 2 sieves. No, these are not just sequences anymore, but they're actually sieves, either upper or lower bound, and we form a new one from them in the same fashion. One can check that in that case, theta d equals theta, the product of these two, where remember, theta was the sum of the lambdas over the divisors of n. Well, what does that mean? That means if these guys are 1 at 1, so is this one. If this one's always greater or equals 0 and this one's always greater or equals 0, then so's this one. So in other words, if we start with two upper bound sieves, what we get's an upper bound sieve. If we start with two lower bound sieves, what we get's an upper bound sieve. If we start with one of each, what we get's a lower bound sieve. So in a sense, this is an important generalization of the starting point of the lambda squared sieve. Now, in particular, let's take the first guy as the Selberg lambda squared sieve of level D. Now, it's a fact of life that this is a very strong upper bound, as we've seen, and it's especially strong if kappa is large, if the dimension, if the sifting density is large. Let's take theta double prime as the almost trivial lower bound sieve we get by taking the first lambda to be 1 and taking the other guys to be -1 for some small primes and 0 elsewhere. That's a lower bound sieve. That's what we did with the sieve of Eratosthenes. We started with all the integers and we threw out multiples of a few small primes. If we only throw out multiples of a few small primes, we still have a lower bound sieve, but its level isn't very large. Well, since this is the product of an upper and a lower bound sieve, it's a lower bound sieve. If this guy has level D and this guy has level psi, then the, is it C in this country? I forget. The product sieve has level D times psi. And it's believable that if psi is small and D is large, that this combination is going to get most of its punch from the first guy. And the first guy's strong. Okay. As a result, we get the theorem of Selberg. Based on these ideas, it just doesn't follow instantly. Based on these ideas, Selberg was able to prove that the sifting limit beta kappa is asymptotically no bigger than what was conjectured. So this is really good. The lower bound is still out by a constant factor. The upper bound is really the more important of the two because it shows you can do something, not that you can't. Okay, for my one final thing I would like to mention, there's been a lot of, I should say I've left out an awful lot of people here. I've been trying to emphasize Selberg's contributions to the sieve. The combinatorial sieves, that's the name Selberg gave to the sieves of the type that Brunn started with, where you just take the Möbius function or 0. The combinatorial sieves have been improved a lot over the years, in particular, most notably by Ivanets. But I wanted to, and some things can be done better with combinatorial sieves now. Some things can be done better with Selberg's sieve. I wanted to mention a very striking piece of recent work that I'm really very glad that Selberg lived to see this work. Let's let Pn denote the nth prime. So the twin prime conjecture is that the lim inf of this difference is 2. Well, we aren't too close to that. We can show that if we divide this gap by the average gap, we get something that's bounded. That follows from Chebyshev's old work. From the prime number theorem, it follows that this is less than or equal to 1. from work of Emeritus, I don't know, a long time ago, it follows that it's less than or equal to some number which is less than 1. Bombi made a big breakthrough in knocking it down to below a half, and if I hope I shouldn't make such attributions when the author's in the audience, but I believe that this was largely a large part of the motivating factor for his prime number theorem, which has been used in 1,000 different ways since then. And over many, many years, this constant was gradually lowered by many people, Huxley, Meyer, and others, to about a quarter. And in recent work, the last 2-3 years, of Goldstein, Pintz, and Yildirim, it's now known that this is 0, and more strongly that there exist infinitely many n such that this gap is bounded by essentially the square root of log Pn. I have a log squared there, and I didn't have room to squeeze in the Pn, but as everybody knows, log is essentially constant. So now I wanted to mention this proof really uses, well, it uses a lot of ideas of Goldstein, Pintz, and Yildirim, but it really uses the Selberg sieve in an essential way. You start off with a product of this form, kappa factors, so where h1 up to h kappa are an eligible kappa tuple. This leads us to a kappa dimensional sieve. By eligible, I mean you don't look at n times n plus 1. You can look at n times n plus 2. And you don't look at n times n plus 2 plus n times n plus 4, and so on. Okay, so you want to find 2 primes in here. If the sieving limit is 2 kappa, you should only be able to find 2 in each. So you have to do a little better. You have to do a lot better. So 35 years ago last September, I made my first visit to the Institute. My first job was as Selberg's assistant, a fact which I have continued to brag about for 35 years. There weren't many young number theorists here that year. There were a lot of number theorists. I mean, if you didn't insist on young, there was Selberg, there was Vey, Serre was visiting, and of course at the university there were Shimura and Iwasawa and that kid named Katz. He was young. But the following year, there were quite a few young number theorists. And so Selberg decided he was going to run a seminar. So he gave a talk. At the end of the talk, he asked for a volunteer for next week. So somebody volunteered. Each week at the end of the week, he'd ask for a volunteer. Eventually, we'd all given talks. So Selberg gave a second talk. Then he'd ask for a volunteer. Well, a few more people volunteered to give second talks. Then he didn't have a volunteer. So he gave a third talk. Well, around this time, we started to realize that if nobody volunteered, Selberg was going to give a talk. And what's more, he'd talk on something none of us had ever heard before, something that had never been published. Well, after that, there were very few volunteers for the rest of the year. So I have to say that a lot of those results have since appeared. A lot of those results appeared in 1991 in his second volume. And we're hearing today, and we're going to hear tomorrow, about a lot of very fundamental advances that Selberg made in various parts of the subject. But I have to point out, I cannot refrain from pointing out that in his 1991 volume, which either published all of his unpublished work the previous 30 years, or that part of it which he was willing to publish, there are 247 pages of manuscript, and of those, 183 are devoted to sieve methods. Thank you very much.